So, mass number. Mass number is defined as being the protons plus the neutrons. Protons plus neutrons. We can rearrange this equation by subtracting protons from both sides of the equation, and then we have that the neutrons equals the mass number minus the protons. This is useful because sometimes we know the mass number, but we want to find out the number of neutrons. It's important to know that mass number is always a whole number because it's protons plus neutrons. You can't have a half of a proton, so it's always a whole number. You can't have half of a neutron, so this is always a whole number. So the mass number is always a whole number. It is not the mass you see on the periodic table. The mass you see on the periodic table has decimal places after that, 2 decimal places after it, and so I don't want you to get confused with that. That mass on the periodic table is an average atomic mass, and I'll give you more information about that later. But right now I want you to focus on mass number, protons plus neutrons. So let's do some mass number practice here. First of all, if you've got the old version of the notes, there's actually a mistake on your notes. Question 1 should have 6 neutrons, not 8 neutrons, which is what the old version of the note says. Let's do example 1 together. An atom has 6 protons, 6 neutrons, and 6 electrons. Which element is it? Well, if I want to know what element I have, I always look for the number of protons. So I want to look up 6 protons, and that tells me that I'm dealing with carbon. And what is its mass number? Remember, mass number is the protons plus the neutrons. So in this example, I want to add my 6 protons plus my 6 neutrons, and that's going to give me a mass number of 12 for example 1. I want you to go ahead and try example 2 and then check your answers with me. An ion has 8 neutrons, 10 electrons, and 6 protons. Which element is it? Remember, we always use protons to define the element. 6 protons, just like before, we have carbon. What is the mass number? We need to do protons plus neutrons. So in this example, we're doing the 6 plus 8. And so this version of carbon has a mass of 14. Notice that the electrons are different to the protons, so this is an ion. It has a charge, and we'll look at calculating the charge later. For right now, we're focusing on mass, and I want you to notice I have 2 different versions of carbon here. I've got carbon with a mass of 12, and I've got carbon with a mass of 14. Both of those masses are different to the mass I see on the periodic table. If I look up carbon, the atomic mass, the average mass, is 12.01. It's close to this, but it's not exactly the same as this 12 that I calculated here. So remember, mass number you get by doing protons plus neutrons. You don't look it up on the periodic table. We've got 2 different versions of carbon. We need to have a way to communicate to each other what version of carbon we're talking about. What's the isotope that I'm talking about? So we're going to learn different notation for communicating about different isotopes. First, let's get a definition of isotope. Isotopes are atoms of the same element that have different mass numbers. Another way to say that same definition is we have the same number of protons, because it's the same element, but different numbers of neutrons, because the mass is different. So if I look at these 3 pictures here, the blue represents protons and the red represents neutrons. All of these atoms have just 1 proton, so all of these atoms are hydrogen. This version, though, has 0 neutrons, this version has 1 neutron, and this version has 2 neutrons. All of these versions of hydrogen have just the 1 proton, but the total mass here is 1. The total mass here is 1 plus 1 is 2. And the total mass here is 2 plus 1 is 3. 3 different versions of hydrogen, 3 different isotopes of hydrogen, each with different masses. Isotopes don't differ in how they behave in chemical reactions. They do chemical reactions just the same as other isotopes of the same element. But they do behave differently in nuclear reactions. Some are more radioactive than others. So it's important to be able to specify isotopes. And we're going to identify isotopes by saying what element it is and by giving the mass number. Kind of like I did here. I gave you the symbol to tell me that I was talking about hydrogen. And I gave the mass number to show that there was a difference in these three different types of hydrogen. So let's learn how to do two different types of isotope notation. The first type of isotope notation we're going to learn about is called hyphen notation. There are three parts to it. We write an element name, we write a hyphen, and then we write the mass number. So an element name, then a hyphen, then the mass number. Remember, the mass number is the protons plus the neutrons. So 6 plus 6 is 12. That's where the 12 comes from. Carbon-14 has a different mass number, 14. That comes from adding together the 6 protons and 8 neutrons that you did on the example previously when we were doing mass number practice. So this is one way to represent isotopes, hyphen notation. The other way to represent isotopes, you've already seen me do for the hydrogen pictures a couple slides ago. This is called the nuclear symbol. There are three parts to the nuclear symbol. First, you write the element symbol. In this case, I'm just talking about carbon. And then the mass number goes in the top left corner, and the atomic number goes in the bottom left corner. Remember, the mass number is the protons plus the neutrons, and the atomic number is just the protons. It is important to know that each corner around the element symbol has a different meaning. So it makes a difference. The mass number has to go in the top left corner. The atomic number has to go in the bottom left corner because each of the four corners has a different meaning. So you need to be careful about where you write each number. As I said, mass number always goes in the top left. Atomic number always goes in the bottom left. If there is an ion charge, we write it up here in the top right corner. And if we have a molecule with more than one of a particular kind of atom, we write that here in the bottom right corner. So, for instance, the oxygen you're breathing right now is not just made up of single oxygen atoms, it's made up of oxygen atoms that have bonded together in pairs to make a small oxygen molecule. It's okay sometimes to leave corners empty. Like, for example, here, the oxygen doesn't have a charge, so we just leave the corner for charge blank. Here's an example that does have a charge in it. This time I've got carbon with a mass of 14. The atomic number is always 6. But here I do have an ion charge, a negative ion charge. Think for a moment. Does a negative charge, would that have more protons or more electrons? More electrons. Electrons have a negative charge, so if you have a negative ion charge, you must have a lot of electrons compared to the protons. The number of atoms goes in the bottom right corner. But here I don't have a molecule, so I've just left that blank, and that's okay. And it's okay for corners to be left blank. The important thing is to use the right corner for the right number. And that takes practice and studying and reviewing your notes. So let's do some isotope practice. I'll do the first one with you, and then you can pause before each subsequent example and make sure that you're doing them correctly. If I'm given a nuclear symbol, I should be able to tell from the nuclear symbol what element I have, but if I'm not totally sure, I can look up the atomic number. The atomic number is 1, which means I'm dealing with hydrogen. So my atomic number is 1, so my number of protons is 1. And as I said, I know that I'm dealing with hydrogen. Next, What other information am I given in my nuclear symbol? Well, this top left corner is the mass number. So I'm going to go ahead and write the mass number down here. And the mass number also appears in hydrogen notation after the hyphen. So I can complete my hyphen notation here in this column. When I'm doing the, when I look at my nuclear symbol, there's nothing up here in this top right corner. Therefore, I assume that this element has no charge. This atom has no charge. When the atom has no charge, then the number of protons is going to be the same as the number of electrons, because the number of positives has to balance with the number of negatives to get zero charge. So I'm just going to have one electron here. So these are equal if there's no charge. If atom has no charge. So I only have one more column to fill out here, and that's the number of neutrons. Remember, neutrons are included in the mass number. The mass number is the protons plus the neutrons. So my mass number is 3, and that equals the number of protons plus my mystery number of neutrons that I'm trying to calculate. What plus 1 equals 3? Well, 2 plus 1 equals 3. So 2 is my number of neutrons. Now that you've seen me work an example, it's your turn. Pause the video and then come back and check your answers. Looking at my symbol, I'm looking at chlorine, capital C, lowercase l. That is element number 17 on the periodic table. So I know my protons, I know my atomic number, and I'll go ahead and write chlorine out over here. I also know that my mass number is 37, so I'll write the 37 with my hyphen notation and in the mass number column. This atom has no charge, therefore my number of electrons has to equal my number of protons, so I'm going to have 17 electrons. And lastly, the number of neutrons. My mass number equals my protons plus my mystery neutron number. What plus 17 equals 37? If this is too hard for you to do in your head, you can always subtract 17 from both sides of the equation to get rid of the 17, and you get the answer 20. There are 20 neutrons in this atom of chlorine. Please pause the video and try the next one. For iodine 131, when I look up iodine on the periodic table, I see that it is element number 53. So 53 is my atomic number, 53 is my number of protons, and when I do my nuclear symbol over here, iodine has 53 protons. I do know the mass number because hyphen notation always gives me the mass number, so that number goes in the mass number column and in the top left corner of my nuclear symbol. Because my protons and electrons are equal, I'm not worrying about the charge yet. We'll worry about the charge a little bit later. So I'll just leave that blank. Lastly, the number of neutrons. My mass equals the number of protons, which is 53, plus my mystery number. Maybe you don't want to do that in your head. Maybe you want to subtract 53 from both sides of the equation, and then you get that your mystery number equals 78. So 78 neutrons, because 78 plus 53 equals 131. One more time, pause the video, and then you can check your answers with me. Here we're not given any information about the hyphen notation or the nuclear symbol, but I am told the number of protons. And so that number of protons is the atomic number, and if I look up 15 on my periodic table, this is phosphorus. I don't know the mass yet, but I know that the nuclear symbol is P. I'm going to go ahead and write a 15 here because I know there are 15 protons in phosphorus. Next step. I see that my protons and electrons are the same as each other. Therefore, there's no charge for me to write in the top right-hand corner. The next thing I need to think about is the mass number. Remember, the mass number equals the protons plus the neutrons. So I want to do 15 protons plus 16 neutrons, so that is 31 as my mass number. So I will write a 31 after the hyphen and a 31 in the top left corner. Let's talk for a moment about that number you see on the periodic table that's called a mass, the average atomic mass. This version that you see on the periodic table, it's a weighted average of the atomic masses of all the naturally occurring isotopes of an element. So it depends on the mass and abundance of each isotope. For instance, we've talked about carbon. There's carbon 12 and there's carbon 14. But if you look up on your periodic table, carbon, element number 6, the number with the decimal places on the periodic table says 12.01. That's very close to 12. It's not very close to 14. That tells us that most of the carbon on planet Earth does have a mass of 12, not a mass of 14. The mass of 14 is quite rare on planet Earth. Now, atomic mass, the one on the periodic table, and mass number are not the same thing. You need to keep them separate in your head. But if you ever need to know the mass or the neutrons, and I haven't told you the other one, then it is okay to look on your periodic table, get that atomic mass, and round it to the nearest whole number. Let me give you an example of what that would look like. If I ask you, how many neutrons does chromium have? Chromium is element number 24 on your periodic table, and I didn't tell you the mass, and I didn't tell you the number of neutrons. So you have no way to know exactly what version of chromium I'm talking about, what isotope of chromium I'm talking about. Therefore, you'll look up chromium on the periodic table, and oh, it actually says 52.00, so we don't even have to do much rounding here. We're just going to assume that the mass is 52. We're going to take that number and round it off to the nearest whole number. So even if it had said 52.06, we wouldn't use 52.06. We would round it off to the nearest whole number. Because this number is 0, it doesn't do anything to the 2. We'll just say the mass is 52. So then, to answer the question, how many neutrons are there? I take that number 52, I subtract the number of protons, which is 24, and I get the answer that there are 28 neutrons. So the mass number isn't the same as the average atomic mass that you get from the periodic table. But if I don't give you the information, you can take the mass from the periodic table and round it to the nearest whole number.